So we are training a neural network to recognize digits from images, and we've already downloaded a database of images of which we can use to train a neural network. But before that, let's first set up a neural network and tell it how it can train itself. For this, we're going to use two Python packages called Theano and Lasagna. The Theano is a mathematical package. It allows you to define and perform mathematical computations, very similar to NumPy, but on high dimensional arrays. So Theano is a package that allows you to work on high dimensional arrays, and these are generally called tensors. Tensors is just a name for an array which has a large number of dimensions, but in fact a tensor can also be used to represent a one-dimensional array. Theano is a Python package that allows you to perform mathematical computations on tensors, just like NumPy allows you to perform mathematical computations on NumPy arrays. Lasagna is a library that is built on top of Theano, and then it allows you to build neural networks. So it allows you to say, this is a neural network which has so and so layers. Each layer should have this many nodes, and if there is some dropout, that is some edges that you should not include, what those edges should be, and so on. It also allows you to do stuff like define error functions, then define how the training of a neural network should be, calculate the accuracy of your trained neural network on a new data set. All of these things Lasagna allows you to do. So make sure you install the latest version of both Lasagna and Theano. In fact, if you install Lasagna, Theano will be installed as a dependency. So you could just go to the GitHub page of Lasagna and find the install command, then run it at your shell or DOS prompt, and you'll be able to install Lasagna. Just Google Lasagna Python, you'll be able to find the page for Lasagna as well as the GitHub page. On the GitHub page, if you just scroll down, you'll be able to find the commands that you can use to install Lasagna. And if you run both of the commands, then it will install the dependencies of Lasagna as well, which includes Theano. We've forgotten to write the import statements here for both Lasagna and Theano. I'll come back and do that later, but before you run this program, you need to have the import statements. So we're defining a function here that's going to create a neural network. This neural network will have two hidden layers. Each of those layers will have 800 nodes each. The output layer will have 10 nodes. Each node will take a value between 0 to 1. And each node will be representing one digit. So the digit which has the maximum value for the output will be the predicted output. The input layer is going to have as many nodes as you would have numbers representing each image. So this is going to be about 784 because each image is represented by 28 cross 28 pixels. We'll let the neural network figure that out. We're just going to tell it that it's going to get an input which is of the shape 1 cross 28 cross 28. For each image, one channel cross 28 by 28 pixels. We will link this input layer to the input var that will be passed in through the build neural network function. So the neural network function will be given an input var which will be something like the training array that we set up earlier, xtrain. And this array will become the input for the input layer. So here we are setting up the input layer. We're going to call it L_in. So Lin is the input layer. We're instantiating a Lasagna layers input layer. We're telling it that the shape of the input is going to be 1 by 28 by 28. And the input is linked to this input var that's going to be passed in through using the build network. Now we are going to say that there will be a 20% dropout. This means that randomly 20% of the edges that connect the input layer to the next layer will be dropped. So in a fully connected layer, what would happen is every input will be connected to every node in the next layer. Instead of that, 20% of the edges will be randomly dropped. This is done to avoid overfitting. So the whole idea of this is very simple. Each time you will instantiate a type of layer. It could be an input layer. Here we are instantiating a dropout layer. A dropout layer will take in which layer that you're going to do the dropout on and the amount of dropout. Here the dropout is 20%. Then if you set up a new layer, that layer will take in the previous layer, which is ln drop. So each layer that you instantiate will take in as an input the previous layer. Here we are adding a layer with 800 nodes, and this will initially have every edge possibly drawn. So that's why we are saying that it is a dense layer. A dense layer by default means that every possible edge which can go out from this layer will be drawn. This takes in the previous layer, which is ln drop, the number of nodes 800, and then some specifications to tell it what the function inside that particular node should be and how the weights which represent each edge should be initialized. So these you can explore in the lasagna documentation. There are many different schemes to do it. Here we're actually just using the default values. We're not changing anything here. So the Glorot uniform scheme is just a way to initialize the weights randomly for the hidden layer in a way that when you train, the weights will reach and converge to a minimum very soon. Now, instead of leaving a completely dense layer, we're just going to add a dropout to this layer, just like we did to the input layer. But to the input layer, we added a dropout of 20%. Here, we are adding a dropout of 50%. Now, the number of nodes that you add to each layer, for example, here we added 800 nodes in the layer. The amount of dropout you do. These are parameters that you can keep tuning to figure out what the best configuration for your network should be. They are like knobs that you can twiddle. You can also change the function inside the nodes. This is what the non-linearity parameter specifies. So we're going to do the exact same thing again for a second hidden layer. So the second hidden layer will just take in the first hidden layer as an input. It's exactly the same. It has 800 nodes. It has the same initialization for its weights. It just takes in as an input the hidden layer instead of the input layer. We're again adding a dropout of 50% to the hidden layer. Now we have the final output layer. The final output layer is going to have 10 nodes, each for each digit between 0 to 9, and each node will give out a value between 0 to 1. We'll look at the max of those values and figure out which digit that particular image is supposed to be. So the number of units should be 10. That's a typo that I'll correct in a second. And we're saying that the function which is in the output layer is a softmax. Now the softmax is just a function that will say that the output should be a number between 0 to 1, and the max of all these numbers will represent the final output. So that's it. The output of the function, the build neural network function, will be the final output layer. Since each layer is linked to its previous layer, the effect of this is that we are giving access to the entire neural network by returning the output layer only. As I mentioned earlier, we forgot to import the required libraries, so let's do that quickly. we need to import lasagna, and we need to import Theano, and we're going to import a module called tensor from Theano. We call that capital T. This is going to be used to instantiate some empty arrays that we're going to use as placeholders while we're going to say how the network should train itself. So each layer in that neural network, the hidden layers and the output layer, have a set of weights that represent that layer. Now, to tell the network how to train itself, that is how it should find all the weights, we need to set up some functions. So the way this works is that we'll set up some functions that tell the neural network how it's going to train itself. And to do that, we'll have some placeholders for the actual training data set. So we'll set up some empty arrays which will act as placeholders for the training data and the labels. And we'll give those placeholder variables to the network while we are explaining how it's going to train itself. So these are the placeholders that we're setting up. The input var is a tensor4, which is an empty 4-dimensional array. The target var is an integer vector. It's simply a 1-dimensional integer array. So both of these are representing the shapes of what the input and the labels are going to be, but they are empty arrays. We'll call the function that builds the neural network with all the specifications that we gave it. 2 hidden layers with 800 nodes each, 1 output layer with 10 nodes each, 1 input layer which takes in images of the size 28 by 28. All of these are specifications that we gave the build_nn function. When we call this, a network is instantiated with all of these specifications. Now we're going to tell it how to train itself. Any training will require iterating through 3 steps. The first step is to compute the error at the current iteration. That will be computed using some standard error function that is available in Lasagna. So first we'll use the network that we built to get the output for the current training set. This will be the current value of the output using the current weights of the network. Then we're computing the error using this categorical cross entropy function. So it will find out what the difference between the predicted value and the actual values of the training set. This categorical cross entropy is one of the standard error functions for classification problems, and it's available in Lasagna along with a number of different functions. They're just choosing this particular one. As an example, you could try out any other function. So this loss is what we have defined to be the error function. Next, we'll tell the network how to update all its weights based on the value of the error function. So the value of the loss. So params is all the weights of the network currently. Get all params is a function that will look at the network and fetch all the current values of the weights. Then we have updates, which is the incremental changes in the weights params. So params are going to be incrementally changed by a certain value based on the error function loss. The increment is going to be a function of this learning rate and momentum. These are again knobs that you can twiddle to figure out what the right tuning should be for the network. Nesterov momentum is one of the options that Lasagna provides for the update of the weights. So how much the weights should be updated in one step. This Nesterov momentum is one of the options that we have. It's basically a extension of this concept of stochastic gradient descent. So stochastic gradient descent we had talked about in some other topic recommendations. Let me quickly recap. The basic idea is you have an error function. Now this error function has a current value based on whatever the weights currently are. if you take the slope of this error function at the current point and you move downwards in the direction of that slope, update the weights so that you are moving downwards in the direction of that slope, then you have reduced the error function somewhat. You continue doing this until you reach a minimum. Then Theano basically allows you to compile a function that's going to represent a single training step. So you're going to tell it that a single training step is going to take in an input variable array, which is the array of images in the training set. It's also going to take in a target variable array, which is the array of labels of the training set. It's going to take in the loss function, the error function, and the updates, how it should update the weights at each step. By calling this function a certain number of times on the same training set, you will iteratively update the weights until you reach a minimum value of the error. We can feed this function now into a loop that's going to train the neural network. Before we do that, we seem to have a typo here. We're just fixing that. There's a comma instead of a period. And now we can check if the function works. It does. We're going to use this train function that we set up to run the training for a certain number of steps. So this train function will be called 10 times, once in each step of the training. You could train it for a few hundred steps ideally, or a few thousand steps. It's going to take pretty long based on whatever your processing power is and so on. So each time it's just going to call the train function and pass it the X train and Y train. X train is the array of images and Y train is the array of labels for the training set. We'll just print out which step we are on so that we'll have a progress marker, and then we'll run this code. At the end of this, you'll have a trained neural network. You can give it a new image and see what the output will be in the next class.